Welcome back. I would like to talk about stability margins within the context of state space control algorithms. So I covered in several videos on my channel, right? You design a control system to achieve a asymptotic stability, global exponential stability, basically making some matrices Hurwitz for stabilization problem, for command following problem. So after designing a control system, it is important to understand its resilience. What I mean by resilience is stability and robustness, right? We would like to have some certain level of gain margin, phase margin, or delay margins. For this reason, we find loop transfer functions of the resulting closed loop system and then find the margins. So I will talk in this video how to find the loop transfer functions. And to find margins, then you can use bootplots or some other commands in the MATLAB. I would like to talk about that. But basically, loop transfer functions that we are going to find L of S, I am going to use it denoted by L. These are related with also this video, bootplot stability margins. So before you watch, you may want to watch this video, that part of that video, around 4 minutes. So the L will be related to T of that video that I explained bootplots and how we find stability margins. Basically, L of S that we are going to find will pop up on the denominator, 1 plus L of S. We call it return difference transfer function. And by looking at L, like in here, we can assess margins of the closed loop system. So before you watch this video, you may want to look at this video, because once again, L of S, loop transfer function, will be related with T of S covered in this video. And in fact, T of S in this video, previous video, is nothing but the loop transfer function. I just denoted it by T. All right, moving forward. Let's look at x that equals to ax plus bu. So x is an n-dimensional vector. U is for now just scalar. We have one control channel for now. I would like to generalize the formulation I am making to multi-channels. And U is some control gain matrix. You can use it pole placement command, optimal linear quadratic way to design K. Again, there are videos on my channel about those. I would like to purely focus here about stability margins. So basically, you have this closed loop system, right? X that equals to ax plus bu, closed by u equals to minus kx. To find loop transfer function, or shortly LTF, we break the loop at the planned input here. Or pictorially, basically, we break it right here. UI, we are going to call it injected signal, U0, or UO, return signal. So you can, instead of using U here, you can use UI, you can use U0 to find the loop transfer function. So mathematically speaking, x that equals to ax plus bui, u0 is minus kx. So I am taking this and going to the Laplace domain, subject to zero initial conditions. And the reason for zero initial conditions is, you may remember, transfer functions by definition have zero initial conditions. So basically we have Sx equals to ax plus bui in the Laplace domain. Or you can send this term to the left. You can group things like this: si minus a multiplied by x equals to bui. Be careful, you are dealing with vectors and matrices, so their order matters a lot. And then x you can calculate as si minus a inverse bui. Now taking this x, putting it to here after transforming this to the Laplace domain, we have u0 output here. Return signal is basically minus k si minus a inverse b multiplied by the injected signal. So we call this L k si minus a inverse b as the L of S loop transfer function. All right, so let's do an example. L of S is k si minus a inverse b. Let's choose an open loop unstable system. Eigenvalues are on the right half plane. B is 0, 1, control canonical form. I am using k using the place command to place eigenvalues to -1 and -2. Once again, on my channel, I cover pole placement, eigenvalue placement. And basically L, this Laplace domain formulation, I am using this MATLAB command. If you look at here, this basically has a, you can represent this in Laplace domain or state space. A is the system matrix coming from here. B is the input matrix coming here. K is the matrix, output matrix coming here. We don't have a direct transmission term, so this is 0. I defined this loop transfer function using the state space formulation. Then I converted to a transfer function. And then I am applying this MATLAB command, all margin of L. You can also look at body plot to calculate margins. I just personally use more all margin command. It directly gives me the gain margin, not in decibels, but in terms of, this regular unit, 0.333, phase margin of 64.317 degrees, and the delay margin of 0.305 seconds. Now, I am considering a stabilization problem. You can apply this to command following problem, basically set command to 0. I am doing state feedback case. You can also do it for output feedback case. I think, basically follow very similar structure. But if you get puzzled, if you want me to cover loop transfer functions more in detail for output feedback or any other problems, let me know. I will be happy to do so. All right, so I would like to illustrate just the gain margin. Basically, gain margin says that, nominally, when I simulate x dot equals to ax plus bu subject to the control signal u equals to minus kx, basically system states x1 and x2 goes to 0, st goes to infinity. This denotes the time. Once again, blue is the x1, red is the x2, since we have two states. Now, here, basically, I multiplied the control gain basically by 0.333. What I mean by that, basically, I go to here, I just inserted a block, gain block here, which is 0.333. And basically, once you do so, you achieve instead of having a exponential stability, you have Lyapunov stability, or marginal stability, you may say. System states doesn't go to 0. And if you go to, basically, if you decrease this gain less than 0.333, your system will become unstable. So gain margin, basically, once inserted to the plant input, since we are breaking the loop at the plant input, indicates that, if you decrease the gain less than 0.333, your system will be unstable. So this is kind of a good indication that, right, for example, in aerospace applications, when you fly the aircraft, control actuators can be subject to icing, so their degradation, their performance gets lower. So, and of course, under ideal conditions, you apply the control as it is. But basically, this is kind of a gain margin. It cannot be less than 0.333. Phase margin is good. I mentioned in the other video that I mentioned at the beginning, I usually use gain and delay margin together. So delay margin here, in this case, 0.305 seconds. I didn't do this in this example, but if you go to here, if you insert a delay here, 0.305 seconds, system response will be Lyapunov stable or marginally stable. So your system this means that your system can tolerate delays at the input up to 0.305 seconds. All right, so this is how we read gain and delay margins and phase margins. And looking at these margins for this example, these are pretty good margins to have. And I would say that the control gain that I choose here has a nice level of resilience with regard to the change if there are some changes at the plant input. All right, so this is just for when you have one control channel. And now how we generalize these things to when you have multiple control channels, right? So when, for example, you control an aircraft, you have controllers to stabilize, pitch, roll and yaw, thrust. So there are more than one control surface. So in this case, we assess each control channels margins by breaking control channels one at a time. So that's the idea. So for this, now I have x that equals to ax plus bu. U is no longer scalar. So if you think B matrix like having columns like B1, vector B2, all the way up to Bm, there will be m by m of them because dimension of B is n by m. So you can rewrite this as from I to 1 m bi ui. So basically this is how each control scalar ui control signal is injected to the plane through their corresponding bi vector, which is they are equal to each other. So to find margins, for example, at the PEAT control input, I am looking at the PEAT control channel, or 1 to n. So I am defining this vector E, 0, all the way up to 0, 1, 0, 0. This is 1 by m. 1 is for the PEAT element, and the rest of this vector is 0. So you can basically, UP is the PEAT control channel. You can find UP by multiplying U by this E matrix. And if you insert U, which is minus kx, you have minus E multiplied by k multiplied by x is your control channel, PEAT control channel, the control signal that you are applying to the PEAT control channel. All right, to dive into more details, and immediately after I will do an example. Basically, I am defining U bar, which is K1, Kp minus 1. I am removing here Kp, okay, I am separating. I will explain this in here, bear with me for a second. Kp minus 1, Kp plus 1, so these are basically rows, are vectors, and Km. So I'm gonna call it K bar, I'm gonna call it U bar. So if you remember our from the previous slide, right, Bu I represented as summation Biui. Now taking this summation Biui, I am basically removing Bpup, so I goes from 1 to m minus 1 Biui plus the PEAT control channel that I am interested to find its loop transfer function to assess stability margins of that control channel. In this case, if you define B bar to be like this, basically, you know, B1 to Bp minus 1, I am removing Bp because it is here, I am separating from here. And U bar, basically here, I am removing the U PEAT control channel from here, U1 to UP minus 1, U plus 1 to UM, transpose, don't forget transpose. So I can represent this Bu, or summation Biui to be B bar U bar. These are the all other control channels, but not UP, plus Bpup. Right now, UP is basically a scalar now. Now the closed-up system we have can be rewritten as x that equals to ax plus b bar u bar plus bpup. I am injecting control u bar here, which is, u bar is minus k bar x multiplied by b bar. So basically using all of these in here, we have a minus b bar k bar x. And so other control channels, I am not breaking them. I am only going to break bpup, so I am just keeping it here. And up control signal is minus ek. So if you look at this, we kind of recovered the same formulation. So let's look at more in terms of a block diagram. Everybody likes block diagrams. I like block diagrams. So x dot equals to a minus b bar k bar. I just separated PEAT control channel using the formulation I just showed you, BPUP. And this control channels, this PEAT control channels, control input is minus EKX. So this is very similar, I will jump to here, this is very similar to this block diagram, right? And we have a different A matrix, different B matrix, different K matrix. So basically we have this div A matrix, niv B matrix, and niv K matrix. So by breaking the loop, similar to how I did it at the beginning of the video, because right now UP is like scalar, loop transfer function of the PEAT control channel is EK, coming from here, SI minus niv A matrix, basically A minus B bar K bar, inverse multiplied by BP. And you can do this process for every control channel. If you have m number of control channels. You can break control channel 1, 2, 3 all the way up to m and look at individually their stability margins. Let's consider an example. Okay, I write this p channels loop transfer function here. I am considering an A matrix 3 by 3, so 3 states, B matrix looking like this. And I have two control, basically m is 2, I have two control surfaces here. First of all, I design gain k using the pole placement command, a, b, minus 1, minus 2, minus 3. So basically, if you close the loop a minus bk, I achieve a desired level of performance and stability. As I mentioned at the very first moment of this video, I now have a control design here. Now I am interested to assess stability margins, how resilient my design is, how robust. I would like to look at individually each control channel's basically margins to conclude if I have a good design or not. For the sake of this video, I am only going to look at first control channel because you can apply the same process for the second control channel's stability margins. I am choosing E to be 1, 0 because I am interested in stability margins of the first control channel. In other words, P is 1 in this example. Now, if you look at here, BP is 0, 1, 0, the control channels B matrix that I would like to assess stability margins. The remaining B bar is just the second one, 0, 0, 1. Now, once you use this pole placement command or place command, you have K to be 6, 6, 1, 1, 1, 2. So K bar basically responsible for the other control channel is 1, 1, 2. And basically LP in this case TF SS, similar to how I did. I am using basically, I am writing this loop transfer function in state space, then converting to transfer function. This is my A matrix here, A minus B bar, K bar. BP is here, and my C matrix, if you wish, EK is here. Basically, this state space formulation corresponds to this transfer function. If this point is not clear, if you want me to make a video about how you go from transfer functions to state space formulations and their equivalents, how you go from state space to transfer functions, let me know. If you know this, basically rewriting this Laplace domain transfer function in this state space form should be very clear. If not, I can make a video, leave a comment, let me know. Anyway, so I have a typo here, two typos actually. All margin commands should be together, not separated. All margin, and this should be not L, LP. I am basically, after I define this in MATLAB, I am writing all margin LP command. And MATLAB returns me a gain margin of 0.1667, phase margin of 71.075 degrees, and the delay margin of 0.207. This should be seconds. And because not degrees, delay margin is defined with seconds. Apologize for the typo. So basically, if you simply simulate this controller, you are going to have, with respect to time, this is the time axis. Black is the x1, blue is the x2, and red is the third state. All states nicely going to 0. Now, for example, if you multiply the gain of the first channel by 0.1667, you are going to see that system loses, it's basically, that channel loses its stability. It's basically have a Lyapunov stable or marginally stable response. And you can also, I obtained again, similar to the previous example, simulation example, I obtained this, I am showing this only for the gain margin. If you go to the first channel and inject the delay of 0.207 seconds, you are also going to have a system response. To make the long story short, first channel, you can decrease, margins wise, you can decrease the gain margin of the first channel up to 0.1667. And system basically will behave, so you're not going to lose stability if you don't decrease this more than this. Likewise, that first control channel can tolerate delays, time delays up to 0.207 seconds. So this is how we read how these margins help us to assess resilience, robustness of our control channels. And first control channel in that regard, I would say that, you know, look at here, we are trying to stabilize an unstable system. We have a control gain. Our gain margin is good, actually better than the previous example. Delay margin, it is okay. And, you know, simply if you have more than 0.2 or 7 seconds of delay when you are applying control signals, it is not feasible, so you need to retune your controller. If not, this is a good phase and delay margins. As this being said, this is how I basically assess the resilience of my control architectures, basically for each channel. And if you want more videos or anything in other related videos with regard to stability margins, loop transfer functions, or any other phenomenon, let me know, and we can go from there. Thanks for watching. Take care.